This was the last slide that you saw, and it was basically a summary and some background information about salicylic acid. And we left off and we said that salicylic acid can be made a number of different ways. So those reactions are very, very large. At least there are numerous different types of reactions that can be used to make this product. So what we're going to do in the lab is we're going to use something called methyl salicylate. So methyl salicylate, methyl salicylate. And methyl salicylate is also known as oil of wintergreen. So when you get this compound, it's going to be found in our refrigerator. It's going to be a liquid, not a solid. And this liquid, I want you to smell of it, because you will smell that wintergreen smell just like a piece of chewing gum or anything that's wintergreen flavored. All right. So what does that structure look like? Well, it's very similar to salicylic acid. It has to be if that's what we're going to use to make salicylic acid, right? So methyl salicylate is going to start off with this benzene ring. Again, that's kind of the common theme that we've been seeing. And then up here is going to be a carbon, and this time I am going to draw it just to make this a little bit easier. That's double bonded to an oxygen, and off of that carbon is going to be another oxygen, and then on that is a CH3 group. And then beside of that is another OH. So we're seeing that this structure looks very similar to salicylic acid, and it would be salicylic acid if this CH3 group was off of there and replaced with a hydrogen. Then that would give us a C double bond OOH, which is that carboxylic acid group that we talked about in the previous video. All right, so that's oil of wintergreen. And the lab is going to tell you that to then take oil of wintergreen and mix it with sodium hydroxide. And I'm going to draw the bond that connects the sodium to the oxygen because we're getting ready to draw a mechanism on how this thing works. And you're going to put this into a flask, and you're probably going to heat it up, and you're going to allow it to react, and they're going to give you some time, and then it's going to say after that point, then this is what you need to do with it. All right. So there's got to be something that goes on here in order to make this salicylic acid. All right, so what's going to happen? Well, I told you that opposites attract, right? We've already briefly discussed this. So the rule of organic is to take a look at negative areas and positive areas within molecules. So that means I need to go and I need to find some of these electrons that might show up in molecules, because those are very good areas for molecules to react. So I'm going to go ahead and find every single oxygen, because I know, especially in other previous videos that we've talked about, that oxygens want two bonds, right? And I'm going to put an R and an R here. As long as they have two bonds, they're happy. And then what gives them the octet, which is the magic number of 8, is 2 pairs of electrons. So every single oxygen that I see, there's 2 bonds, so that means these have electrons, 2 sets. Here's an oxygen with 2 bonds, so that means that that one's got some electrons, 2 sets of them, right? Here's an oxygen with 2 bonds, a hydrogen and something else attached to the ring. So that means I've got some free pairs that are there. And then here's an oxygen, right? It's got a hydrogen and a sodium, so it's going to have a set of electrons on the top and the bottom, 2 sets at least. All right, so now I can get an idea of where the electrons are. Those are the negative areas of the molecule. So if I take a look at sodium hydroxide and I want to assign some charges, it looks like if I split this molecule kind of in half, this is my negative end. So I'm going to do kind of a partial, which is a cursive D, partial negative, and this is a partial positive piece. The same thing can happen on this methyl salicylate. That molecule, there is a positive charge. Now, where is that? Well, it's a tug of war game. That's where it's located. So up here at the top, I see an oxygen here that's pulling electrons away. They're greedy, right? That's why they have the electrons in the first place. So those oxygens are very electronegative, which means electron greedy. So here, if I split this molecule up into two pieces, this would be a partial negative, and that would make that carbon a partial positive in a way, right? But this carbon's getting attacked from two sides, because up here at the top, there's another oxygen, and that's electronegative, which means that that's electron greedy, which means that I can kind of split the molecule there and say this is partial negative, and this is even more partial positive, because that carbon is getting ripped of what it has from two different areas, right? If this was an unhappy marriage, think that this carbon was married twice, and both of its exes are pulling away money from him or her, right? Okay, so that means that that carbon is very short on electrons. And that also means that that carbon is partial positive, one of the most positive areas in the entire molecule. So if these two things react together, I'm getting ready to draw a mechanism. And the way that I do it is I start the arrow at the negative piece. All right, so here's the oxygen, right? And I'm going to start my arrow right here. And I need to point to the area that that oxygen likes. And that oxygen would like that carbon right there, because that's the positive end. All right, well, that's the first step of the mechanism, right? The problem, and what I'll do is that down here, I'll draw this kind of intermediate. Intermediate means this is kind of in the middle. It's not really fully complete yet. So OCH3, and if this happens and this oxygen attacks that carbon and attaches to it, then I see this OH, and that oxygen also has a sodium that's hanging off. Right here is that new bond that gets formed. Well, the issue here is that this thing is not going to be very stable. First off, carbon has more than 4 bonds. We got one to the left, 2 on top, 1 to the right, and 1 at the bottom. That's a total of 5. And then this oxygen only needs 2 bonds. Remember, 2 bonds, the rest of it's electrons. Okay, well, now it has 3. It has the hydrogen bond, the sodium bond, and this new bond that's to the carbon. So this is not going to be a compound that's going to stay around very long, okay? And for that reason, well, we're not even going to draw that out, because if it's not going to stay around very long, then what's the purpose in it, right? Okay, so now I'm going to go back, and we're going to complete the mechanism. So what does that mean? Well, the negative O points to the positive carbon, and carbon has to make a decision. I have too many things. I need to get rid of one. What do I need to get rid of? Okay, well, I can get rid of the OH that just came into the picture. That's one choice. Or I can get rid of the double bond O that's sitting up above me. That's my second choice. Or I can get rid of the OCH3 that's sitting over to the right-hand side of me. That's a third choice. And then the fourth choice is getting rid of this entire ring that sits down below. Well, before carbon makes that decision, carbon actually has a heart. Before the breakup, carbon wants to make sure that its partner is going to be okay on its own. It looks out for him, right? So when this cleave happens, if it cleaves the top piece, the double bond O, it's kind of by itself, and that oxygen's not going to be very stable. It could go crazy. So carbon is very reluctant to cleave that oxygen. That's the only oxygen, only one atom up above it. Not only that, but that oxygen has 2 hands on carbon. And that oxygen is going to make sure that it doesn't go anywhere. So it's really attached to the hip. That double bond is going to be very hard to break, and to basically stay off of the molecule. Okay, down below that huge big ring, there's a lot of buddies that's looking out for that piece of the molecule, right? So on its own, it's okay. The problem, though, is that out of the other options that's here, this carbon or this oxygen, this is the one that's giving it the problem. That oxygen's needy. Why? We already said that oxygen's electronegative. And that oxygen's going to want to pull electrons away from carbon constantly, over and over and over. Imagine dating someone and the only thing they want to do is spend your money. This piece down below, yeah, this is a bigger piece, but there's no electronegativity here. There's not an area of the molecule that's pulling electrons away from that carbon. So even though that this is a bigger piece or a bigger molecule, this relationship is not needy at all. It's not affecting that carbon. So why get rid of it? If you're tired of losing money and spending money, you need to get rid of the problem that's making you do it. So carbon decides to get rid of the OCH3 group. And I have to draw that. I have to show that on a sheet of paper. So the way that I do it is that I start my arrow here on the bond, because that's kind of the negative area. Those are where electrons are located, right? They're not sticks. There's actually electrons that are there. The line is drawn just to symbolize that. So that's that negative area. And that negative area is going to go and it's going to point toward the oxygen. I need to show where those electrons are going to end up. Well, when I do that, that means this OCH3 is going to go off on its own. So OCH3 is now away. And it still has two pairs of electrons. And now it has this pair of electrons that are from that bond. Okay? So I'm going to erase that bond, which was what was connecting it to carbon. And what I'm going to do now is I'm just going to go through and I'm going to draw that with two electrons. Well, that oxygen's not happy. The reason the oxygen's not happy is because oxygens always want two bonds, and right now it only has one. It has 1 and 3 sets of electrons. This thing is fully negative. Now, if you're not really up to par on formal charges and don't really know, how do I determine if things are negative or not? Oxygen has 6 valence electrons, right? So if you want to determine if that oxygen has a charge, and if so, is it positive or is it negative, what you do is that you count every dot all the way around, and you count 1 time for every bond. So 1, 2, 3, 4, 5, 6, and then 1 for the bond is 7. And what you do, you take the valence electron number, subtract it from, or take the number that you just got, subtract it from the valence, and you're going to end up with a -1. That's how we assign charges in these chemical compounds. So we have a full-blown negative now, an OCH3 group that's floating around in the environment or in the container. And on top of that, what we now have is a benzene ring, and on that benzene ring is a carbon with a double bond O. And instead of the OCH3 group that's going to be pointed out here to the right-hand side, it's now just simply an OH group. So this OH group has broken away from that sodium. But you know what? That's okay, because that sodium is going to hang out with this OCH3 that just got kicked off. And this sodium methoxide is going to kind of form a compound, kind of like a salt, sodium chloride. It breaks up in water, right? So this is very, very similar. So that's the mechanism of this reaction, and that's how it works. So the lab directions are going to tell you to, number 1, reflux. And reflux, if you've not done it, you'll see that in the actual laboratory itself. But you're going to reflux it, which means you're going to heat it, and you're going to keep heating it for 30 minutes. it's going to actually tell you to keep heating it until you smell the wintergreen smell go away. And the reason is because methyl salicylate smells like wintergreen, but salicylic acid doesn't have a smell at all. So you know that the reaction has went to completion just by smelling it, using your nose. That's about it. Okay? Throughout the reflux, it's probably also going to tell you to add a little bit of acid. And the reason that we add acid is to make sure that these things stay protonated, right? I need to finish that structure there. So we want to make sure that those things stay protonated. We want to make sure it is salicylic acid. And the reason is because we've used sodium hydroxide in the beginning. And sodium hydroxide is a base. This base is going to react with the molecule, and it's going to give us this structure that we see over here to the right-hand side. Well, I don't want that structure to lose on me. I don't want it to spit off hydrogens on me. I want it to keep all of the hydrogens because that is what it makes salicylic acid. If it's anything else other than that structure, it is not salicylic acid anymore. So, number two, they're going to want you to add acid. And it's probably going to be in the form of hydrochloric acid or something else that's similar. And they're going to tell you to check the pH. You want to make sure that the pH is less than 2. And again, the reason for that is to make sure that all of the hydrogens on salicylic acid are staying. We don't want to lose any of them. If we lose them, it's not salicylic acid and the properties are different. Okay? Now, this reaction can go a number of different ways. The reaction could continue with the addition of acetic anhydride, right? Now, that would then make aspirin as a byproduct or your major product, depending on how you did it. But we're not going to go through that step. We're not going to go through that mechanism, and we won't do that in the lab at all because this lab only wants us to make salicylic acid, and that's where we're going to stop. Okay? So that's a little bit about the mechanism, and that's a little bit about the reaction. Now, what about reflux? Well, the reflux is in the back of your textbook, right? And if you've never done a reflux before, you can turn to the back of your notebook or your lab book to page 609. And it's going to give you a diagram of the reflux apparatus. So it's a boiling flask that sits down here at the bottom, and this is where your sodium hydroxide and your salicylic acid is going to go. And then on top of this is your condenser. And the condenser is going to basically be taking cold water inside of it, and water goes in from the bottom and water goes out from the top. And that cold water circulates through the condenser and out the other end. And that allows your product to be heated. It allows your products to basically go into a vapor and your solvents to go into a vapor. But this cold water condenses it back down to a liquid so you don't lose any of it. So it allows you to heat a solution for a very long period of time without losing any volume as you heat it. All right. Now, that's the refluxes that we see in the laboratory. That's pretty much common. But in industry, your refluxes kind of look like this, right? So these are your typical very tall towers that you would see at these facilities. These really tall towers, on the inside of them, it's basically like a water condenser for a lot of them. You will begin to see cold water being circulated throughout the big, huge industry scale tubing and piping. And that is what will condense and even fractionate sometimes, if you're in the oil industry, your samples from each other. If I take a look at the next kind of operation that it wants you to do, it's the recrystallization step. So if you've done previous labs before you're getting to this one, you might be familiar with recrystallization. But the recrystallization basically means you have the solid salicylic acid now, but that stuff is not pure. And we want a cleaning step. Again, it's shampoo and conditioning. You want to rinse and repeat. Okay, so this recrystallization means that I've got salicylic acid here in the flask, and then I add solvent to it to dissolve it once again. And when I add solvent, I'm then going to make the stuff precipitate out a second time. And when it does, I will get a better, cleaner product because of that. So recrystallization is also found in the back of your lab manual if you need to take a look at more detail on it. But your crude salicylic acid will have impurities. If you try to do a melting point on it, it will not be exact. And if you recrystallize, your melting points will be much better. All right. Now, the drawback here is that it typically will lower your percent yield. That means that the recrystallization step, because you're redissolving the stuff and pouring it through a filter and everything else for a second or third time, maybe, you're going to lose product. You're going to lose grams, milligrams, maybe, right? So because of that, you're sacrificing percent yield. But in exchange, you're getting a pure, cleaner product that you can test. As far as the laboratory goes, you will use boiling water as your recrystallization solvent. So you'll add boiling water to your salicylic acid. The impurities will get released from the crude product, and if you allow it to cool very slowly, those impurities will stay in solution, and your salicylic acid will become cleaner, prettier, and much, much better as far as physical properties go, right? Here's a picture of recrystallization before and after. So over to the left, you will see salicylic acid that has not been recrystallized. And then over to the right, that is a recrystallized version of salicylic acid. That's what you want to go for when you're looking at crystals in a laboratory for the most part. You want to see these long, kind of needle-like crystals. You do not want to see fluff like snow. So those needle-like crystals tend to give you better physical and chemical property test than the fluffy kind of whitish snow over to the left. All right, so the lab scenario here, Natural Nostrums claims that its aspirin, which is made from oil of wintergreen, is more natural than the aspirin made from benzene. Competitors claim that this statement's false and it's misleading. They state that the final product is the same no matter what the source of origin is. So you've been given a sample of salicylic acid made from benzene and a bottle of methyl salicylate, which is oil of wintergreen, obtained from Natural Nostrums. So your job is to make aspirin from the oil of wintergreen and compare the product to the sample of salicylic acid made from benzene. And you're going to compare these products by basically looking at your melting points. So this is your first synthesis lab. This is the first time that you've really went into a lab, taken one compound, completely changed it into a different compound, made something new, and then comparing it to another product that we have ordered from stock. So the synthesis target here, your yield should be greater than 85%. Okay? So that means that when you weigh your final product, that's dry, of course, you want to be above an 85% yield. If not, you're going to get points taken off when it concerns your grade sheet. Next is your melting point error. You do not really want to be less than 3% error in your melting points. So the salicylic acid, we know when that should melt, and your product should be melting about the same time. Your melting point should be around 158. So we're giving you a 3% window from that number, and if you're within 3%, we give you a check mark. If not, we'll deduct points, and you can have a second attempt at doing the synthesis again if you want those points back. All right, so that's all that I have to say about the salicylic acid lab. Now you've got the reaction, now you've got the mechanism, you kind of understand some of the background that's going on and how this stuff is doing its job, and now you have your targets, 85% yield and less than 3% error. So good luck in the lab. Hopefully you'll make very clean salicylic acid. What do you do with the products afterward? You can take them home and put them in a bottle if you want. We don't care. What you do with them at your house, that's up to you. I just wouldn't swallow it or take it. But if you want little mementos from the lab, you're more than welcome to do that. Or you can just simply dump them in the trash.